Today we are going to be discussing the effects of drag force on an object trying to reach terminal velocity. Drag force is proportional to velocity and is always in the opposite direction of velocity. The drag equation is b times v plus c times v to the second. For slow-moving objects, b times v is what you use. For fast-moving objects, c times v to the second is needed. The b stands for the drag coefficient, and that is the equation we will use. Terminal velocity equals mg divided by b. Terminal velocity is achieved when mg equals the force of the drag. My lab group decided to drop 3 coffee filters from a given height to see the effects of drag force on an object trying to reach terminal velocity. We charted the effects on Tracker Pro, and these are the results. This is a position versus time graph of the results we got from dropping the coffee filter from the given height. After graphing our real-world results, we moved to a computer modeling software to see what a perfect scenario results would be. I adjusted the mass to equal the mass of the coffee filter along with the gravity to be equal to Earth's normal gravity. I also inputted the weight, force of drag, force of net, velocity, position, and time equations into the software. After all of the computer coding was completed, the results were modeled and graphed. This is the position versus time graph of our data in the computer model. After both results were graphed, you can overlay the graphs to see that the expected results and the actual results are nearly exact, meaning there is very little human error. You can also see that the drag force being absent causes the coffee filters to accelerate at a much faster pace. So what does all of it mean? As you can see, the object not experiencing drag force will continue to accelerate downward because there's no force acting on in the opposite direction. However, this does not relate to terminal velocity because terminal velocity only exists when drag force exists. Once drag force is applied, you can see that the acceleration is much lower. This is proportional to the fact that terminal velocity will be very low. The reason for this is that the mass is very light, causing mg to be a small sum, and when divided by b equals a very low terminal velocity. What if the object did not start from rest? As you can see, I adjusted the ball's velocity to start from a non-zero number at the time equals 0, meaning the ball is not starting from rest. As you can see, the object's velocity is much greater at the beginning, but begins to become more similar to the original graph due to the fact that drag is acting on it just as it would on any other object. This means terminal velocity will be the same for an object starting from non-rest as an object starting from rest. Thank you for watching my lab, and I hope you enjoyed it.